Welcome. So today we're going to be looking at a solar system in AR. And so this is a little bit of a special solar system because it's rotationally aligned in such a way that the top of Earth is exactly where you are standing. So you can kind of see yourself as being standing on that Earth right there. Okay, so I wanted to break down this project from the end result and working backwards. To start off with, we want to have an accurate, rotationally equivalent solar system map. So we want to have it so that our solar system map matches up with the rotation that is currently in our solar system. In order to do that, we're going to need all of our information in a local equivalent reference frame. The things we need to put into that local reference frame are the exact local position and our solar system positions. We've already focused quite a bit in other videos about the exact local position, so we're going to skip that. We are going to focus more on the solar system positions. And so how we're going to get that is a JPL API. The local position requires us to know where our position is, our GPS location, and where the magnetic north is in order to orient our GPS position. And then we also need to know the time to give to the JPL API. So the JPL API, that's the Jet Propulsion Laboratory. That's associated with NASA. So they have some very accurate information, and we're going to be using their API in order to get the planetary position. They have a database that has thousands and thousands of space objects. So we're going to start with planets, but you can actually start looking at where comets would be and other objects. And so it's kind of nice to have this tool available. It's a good idea to go over the different reference frames. The one that we get from the API is going to be in the ICRF reference frame. So that is the International Celestial Reference Frame, and that is very close to the J2000 reference frame. The J2000 reference frame is taken at noon on January 1st of 2000. Our north pole is the z-axis. We're also going to need an Earth-fixed reference frame. That is going to be our second reference, and we need to do a rotation that is dependent on time. The next one, our local reference frame that has a random north orientation. That is because when you initialize AR, it knows what is tangent and what is perpendicular to Earth's plane, but it doesn't actually know the direction of anything. So we're going to need to find some way of fixing that. And then finally, we'll have one where our reference frame is north aligned. So we will have it in such a way that our north is locking that down. Okay. So to do an overcount, that is 4 different reference frames. We have J2000, we have Earth fixed, we have local reference frame that is not north fixed, and then we have local reference frame with the north pole fixed. Before we go into any of the code, I think it's a good idea to just run over what our end result ends up looking like. So here we can kind of see what it looks like. We have a few different planets floating around. They're floating around in the orientation that they are at this current date. If you wanted to find out what date it is, you could actually do some astronomy here, but that's beyond. So one way that we can judge the accuracy of what we did is we can look at the Earth and the Sun and see whether those two align in such a way that they intersect. And so what we'll notice is that we do have a fairly significant error involved in this particular experiment. They don't align perfectly, so that's something to think about. And if we freeze them all at once, we can see that there's a pretty large spread. It looks like it's about it's between a 10 and 15%, or it's between a 10 and 15 degree spread of what our error is. So it's pretty significant. Yeah, so let's just jump into the code now. Okay, so now jumping into the code, we're just going to have to initialize some things. So we want to load our texture first because textures take a little bit of time to load. So we'll do that, and then we will initialize some of our different values. So we'll initialize the IDs for the different planets, the names for the different planets, and the colors for the different planets. Then we will have some extra initializations that we'll be doing. So we'll have a planetary objects where we'll keep our planetary object, and some name tags. Then we will define our requests that we're going to be making. So this is going to have to get inputted the start date, the end date, and the planet ID. So then we will use the API to get those different values, and we will use a CORS method to do that. And so we have to send it through a proxy. So the thing that's before the JPL is just a proxy that's forwarding it with the header that we were talking about a little bit earlier. Then after that promise is resolved, it will return a value. We need to take the JSON of it. So it is going to be returned in JSON. And so once we get that, we need to do some string formatting. And so basically that's going to be splitting and cutting, and then we will get the vector values of the position, and we will push those into the planetary objects. And so that will be where we're keeping the information on planets. Then we will we'll create a function to start our GPS. We won't actually start the GPS at this location. Then we will initialize the dates. So these are going to be this is the current time, and then we'll get the value for tomorrow, and we will turn those into string formats that we can send to the API. We we will also calculate out the rotation that the Earth has happened from noon, because one of our reference frames is at noon. So we will have to check how much the Earth has changed since noon. Then we have our latitude and longitude. And now we have our promise function. And so this is a little bit of a doozy. We have to make all the requests at not the same instance, or else the server that it will be asking for won't be able to respond. So you'll end up getting some error messages. And so what we're going to do is we're going to just spread our requests out a little bit. So we're going to spread them out so that the server actually has time to respond to them. And then once all those are finished, be scaling them all into a more reasonable number. And then after that, we are going to be rotating them by the Earth's rotation that happens daily. Once we're done that, we have all the information that we can do before we start using some of our sensor data. So this is the part where we're going to paste all of our skeletons. So this next huge chunk of code is just code that we were using before. So it's an extra 100 lines or so, but it's 100 lines that we've done before, so it's nothing new. And so we'll be using that. And so now we need the stuff with the sensors. So we are going to need to create a start function for our different sensors. So we'll just have a setup sensors function. And after that, we will initialize the GPS in that function. And the next thing we need to do is we need to initialize the magnetometer, because we also still need to find out which direction is north from our AR reference frame. And so we will have that. We will paste in the information. So we've previously done stuff with the magnetometer. And so we're just going to be using that code as well. So this next section is also a paste, but we need a little bit of different information from this. So before we were just using the exact vectors, but now what we need to do is we need to get the northern angle. So the angle from our reference frame to the North Pole. And after that, we will call a transformation. So that means once the final transformations has happened, we have collected all the information that we need in order to get this rotation correct. So first up, what we'll do is we will turn our longitude and latitude into radians. Then we will construct rotation matrices with those radians, with those rotation vectors, or we will create rotation matrices with the longitude and latitude. And then what we will do is we'll apply those. We will calculate out the rotation matrices for the northern rotation. The next, we need to swap around some of the axes. So Z we were using as being directly upwards, but from the phone's reference frame, with Z being the distance forwards. So Y is our up axis now. And so we need to do a change of basis. So we're just going to flip around our Z and Y axes and a few of the other axes, apply that magnetic rotation, and then we're just going to push it back a little bit so that it doesn't start where our phone is. So the next thing we're going to do is we're basically going to be adding all the objects. And so how this is generally done is you initialize geometry, then you initialize some float arrays, and those float arrays are going to be the size of the things that we're going to be plotting. Then we are just going to fill out those arrays with the information that we have acquired previously, and then we need to attach those arrays to the geometry. We have to do so we're attaching those arrays to the geometry in 3GS. Then with that geometry, once we have the geometry figured out, we need to kind of make some decisions about the materials that we're going to be doing this 3D image with. And so we're going to be using the texture that we loaded initially and a material that we're going to create with that texture. And then using the shader, using the material and the geometry, we're going to create some points, and then we're going to add that to our scene. So one final thing now that we have that done is we might want to give name tags to all of these objects. So these objects currently are just floating points. And how we're going to do that is we are going to just use some code that we have in an extra file, and then we're just going to add that to the scene. So we're going to add some name tags, and we will add the names to those and the locations. And then finally, what we need to do is we need to add a little bit of extra code to get them animated so they will always be pointing towards the camera. And so what we are going to use is we're going to use a slurp in combination with the quaternion of the camera, and that will actually slowly move our value towards that quaternion that we targeted. So when you finish a project, it's oftentimes a good idea to do some error estimates in order to get an idea of what might be the largest problem in your project. So if we look at all of our different ones, we can break it down. So starting with time related, we assumed that everything was stationary and that nothing is changing very quickly in time, which for the most part is true, but some things are changing quicker than others. And so we look at how much angular change is happening per unit time. And so what we'll notice is that Earth's rotation is actually the largest source of error here. So as we're spinning, that is is causing the largest angular change per unit time. Then we can break that down into translational errors. So we kind of assumed that there was no translational transformations that we needed to make, but there are in fact quite a few, and we just ignored those. And so if we break those down, we'll notice that for closer object, we would need to pay more attention to translation. So if we wanted to focus on nearby satellites, or if we wanted to focus on, for instance, the James Webb Telescope, that's probably going to cause us more errors if we don't actually correct for that. Okay, and then also we have the AR errors. So there's the errors from our accelerometers, which is actually fairly insignificant in comparison to the other errors. So that one's not too important to focus on. Our other errors are very large. And then finally, the largest source of error in this has to do with magnetic fields. So we did a very lazy way of getting the North Pole and doing it northern angle. There is much more sophisticated ways of doing that. And so in order to get an actual accurate result, you probably would want to use one of those more sophisticated methods. So in particular, there's two errors that we didn't correct for, and that's magnetic inclination and magnetic declination. So magnetic inclination, we technically just removed that using a dot product, but that actually is a very bad way of, that ends up giving us a lot more error than we need to have. So there's other methods in mathematics in order to get rid of that would give us better results. Magnetic errors are probably the largest form of errors that we have. And so there's two types. There's magnetic inclination and magnetic declination. So we actually accounted for magnetic inclination, but we didn't do it in a very good way. We just kind of took a dot product and used that dot product in order to calculate out the rest of our results. So we flattened out a huge amount of our actual magnetic measurement. And so if we used some other methodologies, we could actually use that information in order to calculate out where the North Pole is a little bit more accurately. And then the other thing that we did is we completely ignored magnetic declination, which is kind of, as you go further north, there's a larger skew where the North Pole is versus where the rotational North Pole is. And so that we kind of ignored entirely. And so if we wanted to make this more accurate, we should probably focus a lot on that aspect, the magnetic. So the conclusion is the magnetic north is probably the most important thing we forgot to